I'm an idiot. I can't believe I just said all that without having my microphone. I'm a dummy. Good morning, everyone. How are you doing? This is our second to last class together, and we're going to be covering yet another controversial topic for today, and this is going to be climate change. This is one of those things that it's like vaccination. It's controversial because of people and not controversial because of the science behind it. Now, sort of an important thing to note about climate change, it's not just a scientific thing, it's something that really sort of touches all aspects of life, whether it's social science, whether it's criminal justice, whether it's physics, biology, chemistry, humanities. It doesn't matter what sort of field you're in, climate change is going to affect you in some way, shape, or form. And even if you don't think about it, it will. So this is what we're going to be diving into today. We'll talk about climate change. Just as a reminder, if you have not filled out your course evaluations, please do. I don't see these till after the course is over, so it doesn't affect anything in terms of your grade or anything like that. But I do use the feedback that I'm given to help improve myself as a teacher, as well as my slides. So please do take the time to do that. I really appreciate it. So I'm going to start off with this little comic. I found this comic a couple years ago, and I always find it super duper funny. Maybe you don't find it funny at all, but I think it's funny at all. Objects and mirrors are closer than they appear, and you have some guy sweating, and you got creepy climate change running after him. Now, I'd like to start off with this for two reasons. A, it's pretty accurate. It's, climate change is something that is closer than it appears. It was sort of, when it first was talked about in the 90s, it was heralded as something that was decades away. But now it's, we're starting to see the sort of the very dramatic everyday effects in our everyday life on a day-to-day basis. So it is really closer than it appears. And the other thing I like about this comic is it's funny. Again, maybe you don't find it funny. I find it hilarious. And I've seen it dozens of times at this point, so I still find it funny. But climate change is sort of a doom and gloom type of science. A lot of people don't like climate change or talk about climate change because there's lots of bad things. And that's just a sort of the unfortunate reality about something as sort of encompassing as climate change as a whole. So I like to keep it on the light side when I'm thinking about climate change. I want to tell you about all the bad things about climate change, but I want to tell you about all the good things about climate change in terms of what humans can do in terms of mitigating this crisis. Now, when we think about climate change, we think about it as a global problem, and that is certainly the case. But I like to start local because people don't give a crap about any issue unless it affects them in some way, or if it's going to affect where they live, or it affects someone they know, right? And so when I'm doing this, I like to keep things local. And now, if those of you that are doing your geography here, you'll notice the skyline of Boston, right? You got the Prudential Center, the John Hancock Building, right? And you got all the skyline of Boston. Now, this is a picture I took a number of years ago. Does anybody know where this picture is taken that I can get such a great view of the Boston skyline? You would know it if you like hiking. And that is correct. It is the Blue Hills. Medford is actually a pretty good answer too, because there's a pretty good spot in the Fells. That's pretty good that you got it, even though you live in New York City. That's pretty good. But yeah, the Fells has a pretty good spot to take a picture like this as well. But yeah, this is the Blue Hills. It's just south of Boston. If you were at UMass Boston's campus, it would be, about a 20-minute drive down 90. Well, depends on the traffic, obviously, with Boston, because it's Boston. But it's like about a 20-minute drive. It's not very far from our campus. It's not very far from where many of you probably live when you are attending Boston, if you're coming, outside, from New York City, as in the case of one of your classmates. Now, or even, I know some of your classmates are coming in from China. So this is certainly a very local picture. Now, one of the things that you may or may not know is that on top of the very biggest of the hills, at a whopping 600 feet, putting it just shy of being a mountain, there's a weather station, and they've been monitoring weather there since the 1800s. And now, and so one of the things about this is you can see how temperature has changed in this local area over time. So we have temperature on the y-axis here in degrees centigrade and degrees Fahrenheit for us here in the States, since we don't use the whole centigrade thing. And then we have the x-axis is 1820 all the way up to modern times of about 2019. I forgot to pull the brand new one. This is from last year. And we have the 10-year mean in blue and the 30-year mean in red. And now you don't need to be a scientist to understand this. There's two things you need to take away from this graph. One is inter-year variability. right? Within a given year, within a given time frame, you have ups and downs. And that's important to remember. Climate has variability at both short and long scales. That's an important thing to remember. Climate is not static. It varies. And that's an important thing to remember. So that variability, you're seeing ups and downs. It's like, like a heart rate monitor if your heart's going crazy. But the important thing to note here, outside of that variability, is the trend. And the trend of blue and the trend of red is ticking upwards, and it's going upwards steadily. And if you did math about this, you would see that the slope of these lines increases back here relative to here and certainly here. So what you're seeing is from 1800s, again, the start of the Industrial Revolution, all the way up to modern times, we're seeing a gradual increase in temperature. And so we're seeing a change in temperature from about 46 all the way up to 50 degrees. So we're seeing about a 4 degrees Fahrenheit rise in temperature, again, over this 100-year period. Or actually, sorry, a 200-year period at this point. So this is what's happening at the Blue Hills. And when we're thinking about this idea of climate change, this is what we're observing at the global level. We're seeing a global increase in the average temperatures. And this is important, right? It's not just a global problem. This is something that's happening in your backyard. That is if you live in the Massachusetts area. Now, there's an important distinction to make here is this idea of climate versus weather, and people get tripped up on this idea. Now, weather is short-term variation. Climate is long-term variation. And now, weather describes a whole slew of things that you know and you probably hate or love, depending on how much you like weather. This includes temperature, humidity, wind speed, precipitation, whether that's snow, sleet, rain, hail, whatever, atmospheric pressure, sunshine, clouds, storms, and frontal systems. Now, all those are weather. And as you all know, and as every state likes to say, it could be one temperature in the morning and a completely temperature in the afternoon, or completely different weather in the morning and completely different weather in the afternoon, right? Weather changes on short-term scales, right? Yesterday, it was nice and sunny. Today, it's also nice and sunny, but tomorrow it could be rainy and cold, right? That's the weather. Now, climate is all these things, temperature, humidity, so on and so forth, but over a very long period of time, over in a given region. Now, weather, again, can be regional, right? All of New England can have a huge rainstorm, but remember, sometimes some certain pockets will get rainstorms, and sometimes certain pockets will just get sunshine, right? And so weather doesn't have to be on big scales. It can also be on small scales. But the important thing to remember here is climate is on big scales. Climate is on over extended period of time. So if it snows in July, that's weather. That's not a reflection of the climate. If it is 65 degrees in January, that's the weather. That is not the climate. Climate, again, is long-term patterns. And when we think about climate change, or sometimes people, and historically speaking, used to be called global warming, this simply refers to the altered patterns of weather over decades. And this includes warming, cooling, raining, snow, storms, everything. All of these things over decadal scales. So that's an important thing. Again, just because it rains, right? Just because it rains and it's not supposed to rain, that's not the climate, that's the weather. And so with that out of the way, we want to talk about how the earth is warmed. We're going to talk about how we go from an average of 46 degrees on top of the Blue Hills to an average of 50 degrees on top of the Blue Hills. So to do this, we got to talk about how the earth is warmed. And the obvious answer to this, and we've discussed this before, it's all due to the sun, right? Solar radiation from the sun bakes the earth in all this energy, causing a warming of the planet. And remember, that sun isn't just involved in keeping us warm, it's involved with photosynthesis, right? Bringing energy to life, right? And so the sunlight is super duper important as a whole, but it also serves as a way to make the earth warmer. There's two key parts to how the earth warms. The first is the atmosphere, and the second was what we're going to talk about in a moment. It's called albedo. And so the atmosphere of Earth currently, and this is in contrast to what we discuss with thinking about how life originated on this planet. The atmosphere of Earth is about 79% nitrogen, 21% oxygen, and then, about less than 1% of all the other things, including carbon dioxide, argon, helium, anything you can think of, any other gases that can make it into the atmosphere, they comprise that less than 1%. But again, most of the air you breathe is nitrogen. A decent proportion is oxygen. Remember, half that oxygen comes from bacteria, half of it comes from plants. And then we have a very small component of these other gases. So what is the atmosphere as a whole? It's simply all these gas molecules that are relatively densely packed near the Earth's surface. Now, the atmosphere as itself is split up into many different types of sort of layers, depending on how close you are. So when we're thinking about the closest parts, about 10 kilometers up, we have what is called the troposphere. This is where we live. This is where all the weather we think about occurs. This is basically where all the stuff is happening. But as you can see, the atmosphere has multiple layers, including the stratosphere, the mesosphere, and the thermosphere. And so there are many layers to the atmosphere. But when we're thinking about, what matters for weather and climate, we're thinking about this troposphere down here. This is what's really involved with transporting gases and heat and moisture around the globe. So anytime you hear weather or climate, it's really all happening down here in the troposphere. But the thing I'd also like to point out here is that our atmosphere is not very large, right? If you hopped in your car and you could drive vertically at 60 miles an hour, you'd leave Earth's atmosphere in 1 hour, right? So it's not very far to go up and leave the Earth's atmosphere and make it into space. I always find that that fact really striking, right? Because you think of rocket ships blasting off, trying to get out into space, but it's not very far, right? It's something that's going very fast, can do it really quickly. But so that's our atmosphere. Most of the things are happening in the troposphere, as I mentioned. And a key component of our atmosphere is what we call our greenhouse gases. And so we're going to talk about these. You all have probably heard of these at some context with relation to climate change or global warming, whatever you want to call it. So we're going to talk about what they do and what they are. And so as you can see from here, we have carbon dioxide, methane, CFCs, which are chlorofluorocarbons. These are things you'd find in like hairsprays, things like that. Ozone, which you all should remember, is the life-protecting oxygen molecule that helps protect you against UV radiation. And then nitrous oxide. So we're going to talk about these gases. So when we look, at sort of the greenhouse gases that are just naturally in the air, water vapor is the most consistent component of all greenhouse gases, naturally speaking, with about 95%. And we have CO2 making up about 3%, and all other gases making up about 1.4%. Now, when we switch gears and we think about what's anthropogenic or man-made, the vast majority of greenhouse gases made by man are carbon dioxide, followed by methane, nitrous oxide, and fluorinated gases. And so these are our greenhouse gases. This is what they do. Now, we're going to think, what do they physically do? They're there. I'm telling you they're important for how the climate changes how the Earth is warmed, but what do they do? Well, they're called greenhouse gases because they induce the greenhouse effect. And now, for those of you that have ever been to a greenhouse, it can be warm in the middle of winter, right? You can go to a greenhouse, maybe you go to a nursery or something, and it's 70 degrees in the middle of winter. It could be 5 degrees outside. The nursery itself is really warm. And this relies on the greenhouse effect. And this happens not just in a greenhouse, it happens at the global level. Now, the idea being here is with our gases, as well as our greenhouse, light enters the Earth, right? It passes through the atmosphere, or it passes through the glass of your greenhouse. And what ends up happening is one of two things. It either is directly absorbed by the Earth, the surfaces, the water absorb that solar energy, or that solar energy is reflected back up. Now, what the greenhouse gas does, or what your glass on your greenhouse structure does, is it basically bounces that energy back in, keeping that energy in the system. Now, without greenhouse gases, that energy would just bounce off the Earth and return right back to space. But the greenhouse gases basically act as like a goalie. They sort of keep things from getting out. All right, they sort of trap in additional heat. But the idea being is if you have more greenhouse gases, you simply trap more solar radiation. If you have a very thick layer of greenhouse gases, very much like Venus does, you have a very increased capacity to hold in solar radiation. So for instance, Venus has an incredibly thick layer of greenhouse gases in its atmosphere. Now, Venus at the surface averages a temperature of about 872 degrees Fahrenheit at the surface. Again, this is all due to its super duper thick atmosphere. And if you look at the atmospheric composition of Earth versus Venus, you can see Venus has 96% of its atmosphere is carbon dioxide, with only 3% nitrogen. And that's directly in contrast to Earth, which we have less than 1% of carbon dioxide and 78% nitrogen, right? And you see there's just a very different atmosphere. But again, Venus is 800 degrees. The average temperature for Earth is about 50 degrees. It's incredibly different, again, all because of those greenhouse gases. The more you have, the warmer your planet's going to be. That's just basic physics. That's how this works. Now, Now, it might sound bad, right? Venus is clearly, we can't live at 800 degrees, but gases are good, right? They're part of the natural warming and cooling of the planet. Now, they make this world as a whole inhabitable. And so if you do the math, if you look at the mean global temperature with the greenhouse gases, it's about 60 degrees Fahrenheit. If you stripped away all greenhouse gases, very much like Mars or many of the outer planets in our solar system, the temperature of Earth would be 0 degrees Fahrenheit. So it would be freezing. Life would not be possible because all water would be locked as liquid ice, right? Water freezes at 0 degrees Fahrenheit. So they're not so good when they get out of control, as you saw with Venus, but naturally speaking, we couldn't live on this planet. Life couldn't exist on the Earth without these very important gases. And it might not seem like there's a lot of them out there, right? You can't see them, right? But what they do is they provide a very valuable service of warming naturally. But as you saw with Venus, if you get this out of control, well, you have some very bad things that are happening. You have consistent warming. And so that's our atmosphere. It's a really important aspect of how our planet is warmed. But the other aspect of our planet is what we call the albedo. And now the albedo is just a fancy word for saying reflectivity of the Earth's surface. And so the idea being is water, as well as land, is much darker, right? It's blue, it's green, it's brown, right? Those are darker colors. Because they're darker, they absorb a lot of solar energy. So their albedo is low. That's in contrast to ice or contrast to snow, which are very, very reflective, right? They're white. They reflect lots of radiation back up. Their albedo is very high. Now, you all have probably experienced this in some way, shape, or form, right? When it's sunny during the winter and there's snow on the ground, the light coming off the snow can be blinding, right? And that's because of how reflective ice and snow is. It reflects a lot of radiation back. And so the idea being with the albedo is, depending on what the albedo is of your surface, you reflect more or less solar radiation. And you can imagine in a situation where you have less albedo, as you would say in a forest or just a patch of dirt, this is going to be a warmer area than this. So what we end up seeing is places that have very low albedo, like say the tropics. They absorb a lot of solar radiation. They get warmer. That's in contrast to say the polar ice caps or Antarctica, right? Where we have very high albedo, they're very, very cold. And so the albedo acts to warm or cool the planet depending on how reflective they are. Now, this is not just a static thing, right? As you know, in Massachusetts, we get warm in the summer. The albedo is very low. We're absorbing a lot of energy directly from the sun. And during the winter, sometimes we get snow, sometimes we get ice, and it's much cooler in Massachusetts. There's much more solar radiation being reflected. So there are places in the Earth where the albedo is pretty consistent, and then there are places where it is variable, like here in lovely Massachusetts. And so the atmosphere and the reflectivity of the planet are a major sort of source of how the Earth warms and cools naturally. And so most of the sun's energy ends up getting dumped into the ocean. The ocean absorbs about 70% or more, I'm looking at the wrong number, absorbs about 85% of all solar radiation that comes. That's simply just as a function of the area of the ocean, right? The ocean covers approximately 70% of our planet. So thus, based on probability, the ocean shall absorb more of the solar energy. But so that's just sort of how the ocean and the planet as a whole is warmed and cooled. But we're thinking about this in the context, and we're talking about this because we're talking about climate change, and we're thinking about man-made climate change here. And climate is, as I've mentioned, is a variable thing. The climate is not static, right? The climate back when we were first colonized back in the 1700s was not the same as it is today. It's variable, and it certainly wasn't the same 10,000 years ago. So the climate is variable. So I just want to illustrate just a really interesting sort of trajectory of this. So we're looking at the Antarctic temperatures, so down at the South Pole, and we're looking at the days before present. So we have modern day time here at 0, and we have 800,000 years ago at the very back end of this graph. Now, we get this information from looking at ice cores. Ice cores are a great way to trap gaseous and climatic information. If you want to read up upon this, I would be certainly happy to send you sort of how this is done. But just to know, this is all from looking at ice cores in Antarctica. And as you notice is that the temperature here changes. It's variable, right? It's variable over consistent cycles, right? It's coming up and down and up and down, but it's not the same, right? It's not just kind of hanging out at 0. It's coming up and it's going down. And that's the temperature in the Antarctic. But if we look at carbon dioxide in the atmosphere, again, just by looking at the ice, we see that it changes as well, right? It's dynamic. It goes up and down and up and down. But what you will notice about this is that the Antarctic temperature, as well as the concentration of carbon dioxide in the atmosphere, well, they change in step. As carbon dioxide goes down, so does temperature. As carbon dioxide goes up, as does temperature. And so they are inextricably linked in our atmosphere and our climate of our planet. This is an important thing. This is not one of those correlations equals causation things. This is one of the things where they are linked together, right? They are linked 100% together. And this is established through sort of this sort of thing, as well as in modern times. And again, if you want to see the effects of very, very high CO2, just look at Venus, right? Look at this climate change out of control. So it is a naturally occurring phenomena as well. So don't think it's just humans are the only cause of it. It does change naturally, but the way it changes naturally is very different from the way that humans change it. And so there's a couple of sort of natural climate swings that we see. And there's a couple of them are due with how the Earth changes its orbit and how it changes what we call its tilt and how it changes its wobble. Now, the way this works is, as we all know, the Earth orbits the sun. The Earth is as same as the sun and all the other planets is spherical, no flat, right? It's not how it works. The Earth orbits the sun. It's not the other way around. Now, the Earth is sort of an interesting thing. It doesn't orbit typically in a circular pattern. It typically orbits in an elliptical pattern here. But sometimes, about every 100,000 years, it switches from being elliptical to being circular. Now, you can imagine if I'm getting closer to the sun, well, I'm going to be slightly hotter. And that ends up happening. So as the Earth shifts its orbit, again, naturally over a 100,000-year period, the Earth's climate will change. So you can imagine it's warmer here and colder in this orbit. So that's one. Next up is what we call the tilt. And so for those of you that remember back from when I talked about how seasons worked, the Earth currently has a tilt of about 23.5 degrees, meaning it's tilting slightly towards the sun. Now that tilt varies on a 40,000-year cycle, and it ranges between a 24.5 degree tilt and a 22.5 degree tilt. And again, this is just changing how the Earth is facing the sun, which changes seasons. And if that's changing seasons, we're changing climate as well. And then finally, we have what's called the wobble. Now, we think about the Earth, it's massive, right? So we don't feel its rotation or anything like that. But the Earth has a natural wobble on a 26,000-year cycle. It's essentially just where the North Pole is facing varies. And so right now it's currently facing the North Star, but soon, well, I guess not soon, in about 25,000 years or so, it'll start facing a different star. So our North Pole in 25,000 years will be slightly different, again, all due to the wobble of the planet. But the important thing about these is these Milankovitch cycles all change how much and how intense the solar radiation is received at different latitudes on the planet. And so you can imagine if you're receiving more intense solar energy, say we're looking at here in China, well, it's going to change your climate in China, right? It's going to change not just China, it's going to change all of Asia, and it's going to change the planet, right? So these natural cycles, again, they occur every 100,000, 40,000, or 26,000 years, can change the planet. And then there's one other thing that I'd like to mention is this intensity of the Earth's light. So the sun's light. The sun changes its intensity every about 11 years. It's this repeating cycle of ups and downs of being more intense or less intense. But they are very minor intensities of solar radiation. And we'll talk about that in just one moment. Now, another short-term cause of climate change, and so these are very long-term, right? 100,000 years. Now, a shorter term cause is what we call volcanic eruptions. And so you guys all know what a volcano is. Magma from the earth bubbles up, causes big explosions, right? All sorts of cool stuff. So this is Mount Pinatubo in the Philippines exploding in 1991. You might have heard of Krakatoa. You might have heard of Mount St. Helens. There's all sorts of volcanoes over the planet that have been erupting at varying stages. Now, sort of interesting. You can look at the average Earth land temperature here on the y-axis. It's in centigrade. So I apologize if you're like me, you don't think about centigrade. And then we have the time on the x-axis here. Now, you can see we have a couple different volcanic eruptions. So we have Laki, Tamboro, Krakatoa, El Chichon, Pinatubo. You can see that when a volcanic eruption occurs, the planet's temperature drops, and it drops by about 1 degree centigrade. So volcanic eruptions, what do? Well, they spew all this ash, they spew all this sulfur into the air. And what this does is it changes the albedo of the planet, causing the planet to become slightly more reflective, and it causes the planet to cool slightly. But you'll notice is that after a volcanic eruption is over, even something bigger, very, very big, like Tambora here, it causes almost a 2-degree change here. I'm sorry, almost a 1.5 degree change here. It bounces right back in a few years. So climate change can be caused on short term by volcanic eruptions, but long term speaking, volcanoes don't affect at all long-term trajectories of climate. And you can sort of see that here, right? Industrial revolution is about here. That's when we started combusting fossil fuels. And you see the temperatures just going up and up and up. So short-term changes, not major long-term changes. As I mentioned, the solar output from the sun, or what we call sunspot cycles, do change. And these vary on, again, that 11-year cycle. And so we can just sort of look at that here. We have CO2 in the blue line here. It's parts per million. We have the year on the x-axis, so 1860 up to now. Then we have the solar sunspot number. Higher solar sunspot number simply means higher solar output. And you'll see they vary at 11-year cycles, right? Boop, 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 boop. And then finally, we have temperature. And the temperature anomaly simply refers to what's the mean temperature and how much does it vary from the mean temperature at that given time. And by that given time, I mean over this given time period here. And what you'll notice is that solar cycles vary at 11 years, but you'll notice is that the temperature, like CO2, is just increasing. And what you'll also notice is that even though these sunspot cycles happen every 11 years, we're not seeing major changes in the temperature change here. So while solar radiation is variable on these 11-year cycles, it's not affecting the current global trajectory of temperature that we're seeing. What we're seeing is really being driven by atmospheric CO2 here. Again, if you ever question that, just think about what happened to Venus. Venus is, well, it's kind of like hell, right? It's really, really hot. So this is what we're seeing. So sunspot cycles, solar output varies, but in terms of modern changes in climate, again, and I'm thinking modern changes in climate, I'm thinking industrial evolution to now, there's no real meaningful change here. And so that's how the climate changes naturally. And this wouldn't be a very interesting or very long lecture. We would be done now if I was only talking about how the climate changes naturally. So let's talk about how humans fit in. So I mentioned the Industrial Revolution, and this is where all this problem really started. And when you're thinking about the Industrial Revolution, you're thinking about the combustion of fossil fuels. And so what is a fossil fuel? It's simply anything that we dig up from the ground that is essentially fossilized remains of ancient creatures. Now, if we're thinking about something like coal, coal is a fossil fuel. It is the fossilized remains of trees and ferns, plant matter. We think about oil. Oil is the fossilized remains of, sort of the fossilized remains, but the remains of something like algae or cyanobacteria that have died and they've been essentially kept in the earth for a very, very long time, and all the pressure inside the earth is converting them into gas. I'm sorry, gas as in oil, not gas as in like a physical form. And then finally, we have something like natural gas, right? I'm sure you guys have all heard when they dig up oil or coal, they get natural gas, methane. And this comes from bacteria. So those are our fossil fuels. They are non-renewable on a normal timescale. So to make coal, to make oil, you need millions upon tens of millions of years to make coal, to make oil. Natural gas can be produced, in real time because it's all bacteria. But coal and oil, they take millions upon millions of years. And so this is where humans come in. We're digging up all these fuels, we're combusting them, and those byproducts of combusting those fuels are greenhouse gases. Now, just keep this in mind as we're talking about this. Remember this graph. CO2 and the temperature, and at least in the Antarctic here, tracks in step. And this is not a correlation, does not equal causation thing. This is one changes, the other changes in step with it, because they are linked together. Again, think about Venus. So how do we know that the climate is changing faster than normal? So I gave you this temperature record, and you're seeing changes on very long scales, right? So we're doing, so this is about 50,000 years or so, right? We're seeing about a, 10-degree centigrade change in temperature over 50,000 years. But the thing about it is what we're doing is faster than it has ever occurred, right? We've done about a 5-degree centigrade change in 200 years. That's something that shouldn't happen on that time scale. 5-degree temperature change should take tens of thousands of years, but we're doing it in a few hundred years. And that's what makes what we're doing as sort of a species absolutely incredible, because it's not that it's happening. As I showed you, climate change naturally happens. It's what's happening is how fast it's happening. If it wasn't happening as fast as it was, it wouldn't be something that we'd be concerned about. So the important thing to think, if anyone ever tells you that climate change isn't happening, it's really what matters here is the rate. If I'm eating a pint of ice cream and my wife wants to get some of that ice cream, if I eat it all in one sitting, I'm doing it really fast, well, she's not going to be very happy with me. But if I eat that ice cream at a nice leisurely pace, well, she's eventually going to get some of that ice cream. Okay, again, it's all about the pace at which I'm eating ice cream or the pace at which climate change is happening. And so we can look at sort of some data. And so we have parts per million of CO2, and then we have the year, so 2015 all the way up till September 2019. And this is at Mauna Loa Observatory in Hawaii. So this is a long-term monitoring site of CO2. And what you can see is that we have CO2 here. This is the average for the given month, if I'm not mistaken. And what we have here is you see a trajectory from 400 parts per million all the way up to 412 parts per million. And so last August, our CO2 concentrations in the atmosphere were 409 parts per million. This year, we're at 414 parts per million. And so that might not seem like a lot, but remember, it's how fast, this is faster than nature could do it. And there's one other sort of thing about this graph that I just want to point out. And you see how you have this wobble? You have this cycle of ups and downs and ups and downs. So this is CO2 varying as well. Now, it's important to note that there is seasonal variability. So as CO2 comes up, this is what we're seeing in the winter, where things are cold, bacteria, there's no plants doing their thing, and bacteria are starting to decompose all the dead stuff. And so you have an increase in CO2. But once the summer comes, the plants come alive, they start producing oxygen, taking in all that CO2 again, and the CO2 concentrations drop. And so you have this seasonal cycle between winter, summer, winter, summer, winter, summer, winter, summer. So just as a note, CO2 varies on seasonal cycles, but again, the trajectory here is what's important. A 10 parts per million change in essentially 5 years is almost unheard of in the geological records. So again, it's all about this rate. We do things super duper fast. And so if you sort of thinking, oh, this is a 5-year period, what happened, since humans came around? Well, I can show you that as well. So we can look at the world population as well as greenhouse gases. And so we have world population here in green, it's in billions. So you see that exponential growth that we talked about in our population lecture. We have CO2, we have nitrous oxide, and we have methane. Again, these three are our major greenhouse gases here, CO2 being the most important. Now, you can see once humans come along, they essentially explode. But you also notice that there is a background level here, right? There is nitrous oxide, there is CO2, there is methane being produced naturally. But you'll see that humans are just essentially causing these to exponentially increase. So this is where the humans come in, or the humans. This is where we come in. Not the humans, not like we're aliens observing humans from space. No, this is where we come in. These gases, again, they're present naturally in nature. These are all derived from biological activity, but you notice that they're increasing in a way that they shouldn't be. This doesn't usually happen in nature. Exponential increases like this in atmospheric gases just does not happen. You don't have enough bacteria doing these processes to put this much gas in the atmosphere this fast. You need something else, and that something else is us. So as I mentioned, all these greenhouse gases come from the combustion of fossil fuels. And so if we look at the greenhouse gas emissions by gas and sector, the gas output looks like this. So in the United States, 82% of our greenhouse gases are CO2, 10% methane, 6% nitrous oxide, and then 3% of all the other stuff. We're not going to really focus on this other stuff. They're not really that important, and they're kind of difficult to discuss. So we're just going to focus on these three big ones because they're doing most of the warming. If we break that down in terms of where it comes from, 29% from transportation, 28% from power, and 22% from industry. And then there's, residential, powering your lights, 5%, commercial, businesses and stuff like that, not like businesses as in anything but industry, like stores, things like that, offices. And then finally, agriculture being 9%. And so this is where it's coming from. This is what we're producing. But you'll notice is that the vast majority of it is to power our societies, right? To get us from point A to point B, to make energy for us, and to power factories, to power making things in this country. And you can imagine this sort of dichotomy exists in other countries, but it might be more severe, right? You might see more, because places like China, India are incredibly heavily industrialized. Well, industry will likely account for a bigger piece of this pie here. And we can look at CO2 emissions over the globe, and they look very similar for greenhouse gases, other greenhouse gases as well. But you'll notice is that we have, this is average CO2 emissions per capita, measured as in tons of CO2 per year. So lighter colors are very low emissions, darker colors are very high emissions. And you'll notice a couple things here. The United States is on fire, and as is Australia. Australia is on fire because it produces a ton of coal. They're one of the leaders of coal production on the planet. That's why they're on fire here. Us, we're just very heavily consuming population, but you'll also know that it's pretty consistent across the planet, right? Most people are producing lots of CO2. And then places that aren't producing a lot of CO2, like sub-Saharan Africa, they're not doing too great in terms economically. And there is actually this really interesting relationship. You can look at GDP per capita and CO2 emissions per capita. And as you increase your GDP per capita, you increase your CO2 emissions. And so you see places that are doing really well economically, the United States, Saudi Arabia, the UAE, right? They're doing well economically, they're producing a lot of CO2. And so there is this direct link between how well you are doing and GDP-wise, as well as how much CO2 you're making. And there's other places like, this one always gets me, Trinidad and Tobago. They're doing a lot of this because of tourism. And started burning lots of coal, just as a note. People always ask me about this one, and I had to look it up because it was so bizarre to me. But that's sort of why Trinidad is there. It should be much lower overall. But again, they have a very high GDP per capita, and that again, there is that nice relationship here. The richer you are, the more CO2 you're producing, the more methane you're producing, the more nitrous oxide you're going to produce. And again, we can look at the past. Just to sort of reiterate this is what these ice cores look like, right? Giant cores of ice taking from the Antarctic. You can look at these to get the temperature, to get the CO2. And remember, this is what we look like. CO2 and temperature are in step. So as humans are burning more and more fossil fuels, we're producing more CO2, the planet is going to change. The climate is going to change. This is what we know throughout history. 800,000, well, this graph is 400,000 years, but I showed you one for 800,000 years. They are linked together in step. So the conclusion we make from this is more greenhouse gases equals more trapped solar radiation and more warming at the global scale. Now, it's important to note that we're thinking about climate change, and it used to be called global warming, and some people still call it global warming, but scientists call it climate change. And it's a global phenomenon. And we used to call it global warming because we would only talk about the news outlets would really only pick up places that were warming. Now, as I mentioned, Earth's climate is dynamic. The planet is dynamic. And what you'll see from this graph is the temperature difference in 2016 compared to the previous 100 years average. And you notice most of the planet is on fire, right? Most of the planet is warming. But you'll notice some parts of the planet are cooling. And that's an important thing to mention. This is why we talk about it as climate change, not just global warming, but the climate as a whole is changing. It's not just getting warmer. Some places are getting cooler. And you'll notice that some of these places, right up in the northern Atlantic, here in sort of near the Korean Peninsula, Australia, right? There's places that are cooling. And that's an important thing to recognize, right? It's not just everything is warming. Most of the planet is warming. As you notice, most of the planet is on fire, but there are some parts that are cooling. And so the planet's climate is changing, right? It's a dynamic system. You might warm something down here, and it might cause cooling over here. And again, there's all sorts of patterns of weather, oceanic currents, wind currents that, again, makes Earth's climate dynamic. And that's important. Just remember, it's climate change because the climate as a whole is changing, not just everything is getting warmer. But again, the prevailing trend here is overall warming. And This trend of warming is not some one-off thing. It's every measurement from every major government, from every scientific body, from every scientist out there shows that the temperatures are rising. So we have the temperature, we have the timeline here, we have the temperature anomaly. Again, that's relative to the average of this time. And you're seeing that we're having this increasing levels. So the war, no matter who you ask, what country, no matter what scientists you ask that measures these things, it's all getting warmer. And that's an important thing. Scientists, again, we like to critique each other. We like to beat up on each other, but everyone is agreeing on this one topic. And that's an important thing, right? Good science requires consensus, right? We know that treatments work for cancers because of consensus of science, right? Good science is robust, it's large. Consensus tells us this, therefore it likely is that. It's the same thing with vaccines, right? All studies point to vaccines being effective and safe. That's why we should trust vaccines. And the same thing here. All these scientists, all this data is pointing to warming. That's why we should think about it as a current thing. Now, we've been talking about how things are projecting. What do things look like in the future? And climate change, again, historically speaking, it was a future problem. We didn't need to worry about it. Well, that's not true, as I mentioned, but what does it look like going forward? Now, there's all sorts of ways we can think about this. So this is based upon this really nice website called Climate Action Tracker. These are based upon the International Panel for Climate Change, or the IPCC. So these are projections going into future. So we have global greenhouse gas emissions. It's in gigatons of CO2. So for those of you that don't know what a gigaton is, it's like 10 to the, was it 10 to the 13 tons? So it's a huge amount of CO2. And then we have time on the x-axis here. Now, we have a couple different scenarios here. So if we don't change anything, really, we have, we enact no policies. We have what we call business as usual. We see that we're likely to see a baseline warming of 4 to 5 degrees C. And again, this is right in step with CO2. If we enact, say, current policies such as the Paris Climate Accord, we only expect to see 3 to 3.5. If we do much better stuff, we expect to see much less temperature change. And so basically any situation you see in the future, we're seeing warming. And in fact, no matter what we sort of do, we're going to see some level of warming. And I hope that's sort of clear here, right? Because of all the CO2 we've put into the atmosphere, we're going to see some level of warming. Sort of the unfortunate thing about CO2, it's a very, very long-lived gas in the atmosphere. So even if all humans were wiped away from the planet tomorrow, that CO2 persists in the atmosphere for tens of thousands of years. So we're going to see some warming. It doesn't matter what we do, but it's really about how much warming we're going to see. Are we going to continue doing what we do and go to 5 degrees, or are we going to continue? Are we going to try to make things and limit it to 1.5 or 2 degrees? It just depends. So that's the projections we're looking at. We're going to get warmer no matter what we do. So what does this mean for you? What does this mean for the planet? We're going to talk about a couple different things. So the first one we've already discussed in class, and you had a homework question about it on your very first weekly problem set. And what are the direct effects of more CO2 on the ocean? Now, as you put more and more CO2 in the atmosphere, a lot of that CO2 dissolves in the ocean. Now, once things dissolve in the ocean, one of the things that happen is they react with water, and they form a very weak acid called carbonic acid. And this weak acid then combines with carbonate to make bicarbonate. Now, the idea being here is what critters make their seashells out of, so crabs, corals, oysters, things like that, is carbonate. So if you have all this CO2 and mixing with water in this carbonate, they're essentially breaking down the shells of our oceanic creatures. So they're making the water, as you dissolve more CO2, you're making the water more acidic. You're dissolving the shells of our creatures, our corals, our bivalves, things like that. And you lead to situations like this. So you have very high levels of CO2. You take a nice, happy coral reef, and you essentially drive it to the point where all the coral dies off. And this is true for corals. This is true for mussels, bivalves, crabs, lobsters, anything you could think of with a nice hard shell that relies on carbonate is affected by higher CO2. Because again, we're making the ocean more acidic. And remember, the pH is a log scale. So a very small change in the pH has huge effects on biology, as we discussed with acid rain. So it's kind of a big deal here. As we talked about, air pollution is kind of a big deal as well. So as you put more and more CO2 into the atmosphere, you're also putting more pollution, right? Because remember, pollution is just as a result from the combustion of fuel. And CO2 is produced from the combustion of fuel. And as we talked about, air pollution produces a huge tax on the human physiology. Well, actually, not just human physiology, all physiology, but we're thinking about humans here. But as you'll notice is that we have this pyramid of effects from air pollution, where we have all sorts of things: lung function, respiratory systems, doctor visits, lost work, lost school days, ER visits, death, right? All these things that are associated with air pollution. And we talked about this already when we thought about public health, but air pollution produces a huge tax on the health of people. And you can imagine if, air pollution becomes worse, as it's potentially projected to be, well, more deaths are going to occur, more hospital visits. And if you have more hospital visits, it's going to tax our healthcare system even more. And I think COVID has already shown us that our healthcare system, not even just here in the United States, but globally, is not really prepared to handle large events. And if you're putting more people in the hospital because of air pollution, that's not going to be good. But more importantly, all these lost work and school days also means loss of GDP, right? You lose businesses, you lose money if people are skipping work because they're sick or not going to school. And again, as I mentioned, air pollution does produce a huge risk to global health. It's estimated that the current level of global air pollution will take off about, on average, about 2 years of a person's life just because of pollution. So you're losing 2 years of your life just because of pollution, and that's even more than someone who smokes for 30 years or does hard drug and alcohol, or uses hard drugs and alcohol, right? And so pollution is gonna take years off your life, unfortunately, and it does. Working days, and it does affect your GDP. So we can look at the loss of working days in 2010. This is in millions. This is just in the United States. This is from the U.S. Commerce Department. We lost 1,200 million days due to air pollution in 2010, and we had again 4,930 million days of restricted activity, and then another 630 million days of minor restricted activity. And now you can imagine, that's modern times, that's 2010. In 2060, when we have higher CO2, more pollution, that's going to be even worse, right? You're essentially seeing a tripling in all three of these categories. So you can imagine, if you have lots of people missing work, that already affects the global economy by billions and billions every year. What's going to happen when you triple that? What's going to happen to global economies? And so there is an important thing here. There is a dollar value here. There really is. People don't like to think like, oh, it harms business to address climate change or to reduce combustion of fossil fuels. But in reality, all these things are actually directly harming. And so there's really, no good reason due to loss of work and healthcare and all that stuff to not really address this issue of higher CO2. As we talked about, we know that the Earth is getting warmer. But what does warming mean for ecosystems? Well, there's a couple different things. So one of the most important ways that warming is directly affecting ecosystems is simply affecting the microorganisms. Now, this isn't just me being biased because I love microbes. It really is the most important way warming is affecting ecosystems. Now, just the way microbes work, as you increase the temperature, you increase their activity. That's just the way microbes work. A 5-degree increase in temperature increases the microbes' activity by about 10 times. So that's just the way microbes work. It gets warmer, they get more active. Just how they do. Now, this is important not just here in Massachusetts, right? Warming, if we warm our soils, our microbes go crazy, and when they're going crazy, they're starting to break down organic matter, releasing more CO2. That's what's happening in your backyard. That's fine. But one of the things that this is really unfortunate about is what happens in places that were not defrosted before. So if we go back up to the Antarctic, or the Arctic, I should say, we look at a couple different things. Many of you have probably heard of what's called the permafrost, and this is soil in the Arctic that is permanently frozen. Frozen, frost, right? Frozen, right? So permanent frozen. So the I stop saying the Antarctic. The Arctic has what we call permafrost, permanently frozen soil. And this is directly under what's called the active layer. And the active layer is where the microbes are doing their thing, where plants are growing. Now, under climate change, this active layer is expected to expand, and it actually already is expanding. It's expected to expand into the permafrost. And so the idea being here, warmer temperatures means more microbial activity, which means this permafrost layer is going to start to get warmer. The microbes are going to start to eat through this permafrost layer. As it gets warmer, the microbes are going to eat more and more and more. And what's going to happen when these microbes are eating more and more food? Well, they're putting these greenhouse gases into the atmosphere. They're putting carbon dioxide. They're putting methane. They're putting nitrous oxide directly into the atmosphere. Now, what does that do? It warms the planet even more. So this forms this really vicious what we call a feedback loop, where climate change is causing something to happen, and what it's causing to happen exacerbates the effects of climate change. So the idea being here, we have high levels of greenhouse gases, increases the amount of warm days in the Arctic, which causes more thawing, which causes more microbial activity, which causes the release of more greenhouse gases, which then go back into the atmosphere and cause increased warming. And you have this vicious feedback loop here, where climate change is causing microbes to go crazy, which releases more greenhouse gases, which causes warmer temperatures, which causes microbes to go even more crazy. And so we have this, what's called the feedback loop, and this is pretty common across the planet. We see this not just with microbes, we see this with the melting of sea ice as well, and we'll discuss that in just a moment. But I also want to mention, because I know you guys like polar bears and you like, things that are cute. Well, everyone likes, that's not just you guys. Everyone likes polar bears because they are adorable. Now, there are direct effects of warmer waters on biology. So it does change all sorts of biology. You can think about polar bears. Warmer weather means less ice for them. If there's less ice for them, that means they can't hunt seals. And as we talked about, if you change a food chain, if you change a food web, well, that can cause the ecosystem to change completely. So I don't want to spend a lot of time talking about this because it's kind of complicated. So I'm just going to note that there are direct effects on the biology of organisms, both through changing predator-prey interactions, but as well as sort of on the biology as a whole. And again, sort of the final thing I'd like to talk about with warmer ecosystems is what's happening to coral. And so for those of you that have been following the news out of Australia, the Great Barrier Reef has seen some of its grading coral bleaching events of all time. So at one point last summer, 90% of the Great Barrier Reef was bleached, and it's because the waters are so warm, it causes the corals to get stressed. They expel their symbiote, causing them to turn white. And so there are direct effects on the biology of organisms. Now, that's effects on biology. Now, a direct effect of warming planets is rising seas. So as water warms, it expands. And now I shouldn't have to explain why, because we talked about why this was early in the semester, but I'm going to reiterate what it is. As water warms, it expands because the idea of warmth is simply a measure of how fast molecules are moving. As molecules move faster and faster, they take up more volume. So as water warms, as the oceans get warmer, as lakes get warmer, their water levels expand. So there's a natural expansion of water as it gets warmer. And what this leads to is rising seas. And I'm sure you guys have all heard of sea level rise. And so this is what we're going to talk about now, expansion of seas. Now, we can just look here. This is some from Climate Action Boston. So we have days of coastal flooding, and we have these 10-year periods. So the 50s, 60s, so on and so forth. And we have days of flooding. So blue is what have occurred naturally, and those are pretty consistent over these 4 decades, or 5 decades, I should say. And then we have those that are driven by climate-linked sea level rise. And you'll see that, well, they're there, but in the past 10 years, we've had a rapid, almost a 5-time increase in the amount of climate-linked sea level rise here in Massachusetts. So we have more days of coastal flooding here in Massachusetts. The idea being is, as the sea level rises, it allows water to intrude into places it never could before. And that's not good, right? If you guys remember back from our population class, remember, close to 60% of all humans on this planet live within 50 kilometers of the ocean. So if the oceans are getting higher, the levels, it means water is going to get deeper and deeper, which means it's going to be more dangerous for people to live in coastal areas. And this is here in Massachusetts. But globally speaking, we know this is going to be a problem. And now I like to show this figure, this picture of Morrissey Boulevard. Many of you, maybe you haven't been down here in probably a while since UMass closed in April or March. But this is Morrissey Boulevard. This is a winter snowstorm, and you see Morrissey Boulevard is flooding. Morrissey Boulevard is relatively low in terms of sea level. But this level of flooding on Morrissey Boulevard, well, it never used to happen as frequently as it does. Now, anytime we get a large storm, Morrissey Boulevard floods like crazy. And it's not just down, at the major intersection where UMass is. They fixed that problem, but it's down here near the bridge at UMass on Morrissey. So this is what we're seeing here in Massachusetts. We're seeing more coastal flooding because sea levels are higher. And we can look at this globally as well, not just in Massachusetts. So we have tidal gauge measurements and sea level change. And we see 1970 all the way up to 2010. And we see tide gauges are showing the levels of the ocean are rising and rising and rising. And it's been about 6 or so centimeters, or about 2.5 inches or so since the 90s. Now, that might not seem like a lot inherently, right? 4 centimeters, 5 centimeters, 2 inches, right? That doesn't seem like a lot. But when you think about it at the global level, it's actually kind of striking. So when we think about tides, right? When we see a tide is like 13 feet and then it drops down to 6 feet, right? We have a 6-foot change in water outside, say on Morrissey Boulevard. That's all due to a 1.5 or 2 inch, a half an inch change in the Earth's water level due to the pull of the moon. So all the tides on this planet are caused by a half an inch tug by the moon, causing the levels of our ocean to increase by half an inch. So again, 4 centimeters doesn't seem like a lot, but half an inch, 1.25 centimeter change is what causes all the tides on the planet. So it really is, it doesn't seem like a lot. And again, 4 degrees C doesn't seem like a lot, but for the planet, for the physics of the planet, it's a lot as well. And so one of the sort of things we see with sea level rise is it's not uniform. Some levels are, some places have sea level change being faster. So we have changes in sea levels between 1993 and 2018. Red is a drop in sea level. Blues are a increase in sea level. And you see the vast majority of places are increasing in their sea level, but there are some places that have dropped. But one thing I'd also like to point out is some of the places that are most hard hit is actually here on the East Coast, as well as here in Southeastern Asia as well. So there's climate, the sort of the global seas are increasing in their level. And we can ask the question is, what's causing it? Why is the planet getting, why is the ocean becoming sort of higher, right? And there's a couple reasons for this. And so we talked about thermal expansion, water getting larger as it warms, right? Water, if you took a pot of water and you measure the volume of it when it was room temperature versus when you boiled it, it would take up more volume. And that's what's happening. Thermal expansion of water because of the planet getting warmer is just a thing. Now, what's really causing the major changes in sea level is two things. It's just one thing. It's both things, but it's just the main driver here is added water. And that added water comes from the melting of landlocked ice. So the melting of glaciers. So what we're seeing here is all this fresh water that's usually locked up in glaciers that's hanging out over land is melting, and it's melting and draining directly into the ocean, or the ice is moving from land directly into the ocean where it then melts. But that's what's causing it, the melting of landlocked ice. And the biggest sort of source of this is going to be up in the Arctic, in particular Greenland. Greenland is the biggest source of meltwater from glaciers in the world. And in fact, there was actually a recent report out from some scientists that showed that Greenland is irreversibly melting. It's not going to ever bounce back to where it was before because of man-made climate change. So just to go back here, the meltwater from glaciers plus thermal expansion of water is what's driving the expansion of our global seas. And it's sort of an unfortunate thing. Our sea levels are getting higher. But what does this mean? Well, the figure people like to use all the time is the projections of Florida, because Florida is a low-lying area of the United States. But what you can see is Florida in 2001 and Florida in 2100. That is provided, we don't do anything to stop climate change. And this is what Florida is predicted to look like if sea levels rise by, if I'm not mistaken, by 1 foot. And that's 1 foot, right? That doesn't seem like a lot of water, but look at how different Florida is. The coastlines, these low-lying areas are basically gone. Big cities, Miami, from doing my math, Florida, Orlando, right? All these big coastal cities are going to be gone. And that's not just true here in here in Florida. We can look projection globally. So if we got rid of all ice, globally, we can look at the United States. We can look at a projection what the United States would look like if there was no ice left. So climate change was unchecked. And you can see that, well, Boston, New York City, DC, Charleston, Houston, right? Huge parts of the country would be underwater. And that's not a good thing, right? Millions, tens of millions of people live in these big cities that would be inundated with seawater. So clearly not good. But let's think about Boston, because this is where we are, right? We're down here on our lovely peninsula. What does this mean for Boston? And luckily for us, Boston takes climate change very, very seriously. So if you want to take a peek at Boston's website, they have their climate ready action plan, and they have all these cool maps you can play around with. But let's look at Boston's projections. So business as usual, 27 high tides. This is what we're seeing. We're seeing parts of Boston being inundated with water, including Logan Airport, even parts of the peninsula where UMass is, the Harbor Islands, right, and Boston proper, North End, right, things like that, right. So we're seeing high tides, again, just because of sea level rise, going into places that are heavily, heavily populated. We can look at coastal flooding, so days that essentially flooding that would happen due to storms, and you'll see that, again, places are being hit pretty hard. We expect to see much, much more flooding in Boston than we would without sea level rise. And then we can sort of just do this really interesting overlay here in Boston where we have coastal flooding, high tides, and economic and social vulnerability. So economic vulnerability simply refers to areas that are poorer, doing less off economically. And social vulnerability include, people with disabilities, the elderly, things like that. And you can see the sort of unfortunate reality of this is that they line up really well. So people that are actually in Boston that are going to be hit hardest by coastal flooding and high tides are going to be the people that are economically struggling, are going to be the elderly, the sick, the disabled. And so there is this direct relationship, especially here in Boston, but also globally, between those that are not doing as well and the most severe effects of climate change. So again, this is, if you want to just sort of take a dive into these maps, they're really, really, they're not fun, but they're very, very informative to sort of see the projections of Boston. And this is, a lot of cities have this. So, I would imagine if you're in New York, they have something similar that you could check out for your own city. So. Now, in direct tied to coastal flooding, we have this economic problem as well. As I mentioned, so many people live near the ocean. One of the things about living near the ocean is that your property is more valuable. In particular, you're thinking about the island of Manhattan, right? Boston, the Cape, all of Connecticut, New Jersey, right? All these places that are heavily populated that have millions and billions of dollars of economic value. Now you can imagine if we have higher seas, water is penetrating into areas, it's going to make that property less valuable. It's going to cost people billions and billions of dollars. So again, there is an economic incentive here for this as well. And so we sort of next up on this is climate and disease. And we've already discussed this. Warmer temperatures means more mosquitoes, means more mosquito diseases, means worsening of diseases. We're not going to discuss this again, but just as a reminder, climate and diseases are linked together. There's sort of another direct effect of this is water shortage. So I live in Easton, and what we see every year in Easton and many, many towns around Massachusetts is we see water restrictions, water bans. So you can only use water so much. And the reason this is because, well, things are getting warmer. We can take less water from the ground. We can take less water from aquifers simply because there's more heat. The planet is getting warmer. As the planet warms, as we discussed when we talked about weather earlier in the semester, more heat equals more evaporation. And if there's more evaporation, that means there's less fresh water. That's just sort of the reality of it. As the planet gets warmer, fresh water is going to become more scarce. Now, a great portion of the planet already is experiencing what we call freshwater stress. Now, freshwater stress is simply, I don't have enough to essentially sustain my population in a meaningful way. Meaning like I'm struggling already to pull up, I'm pulling up too much relative to how much water I have, or I don't have enough water to essentially pull up to sort of dissipate to my population. Now, as we all know, water is 100% vital for all life. It is, in my opinion, a basic human right, and not just my opinion, a lot of people think that too, but it is a basic human right. What you'll notice is that we have freshwater stress here on 1995 and projections in 5 years from now. I like to think this one's farther away, but it is 5 years from now. And you see the amount of freshwater stressed areas isn't growing. So we're getting, this map is getting warmer in colors, which means the amount of freshwater stress is growing. And we're starting to see this already here in the United States. The Mississippi River is at an all-time low. Our aquifers here in the United States, our lakes are at an all-time low because of, again, taking so much water because there's warmer planet, more evaporation, less fresh water. And if you keep taking and taking of water, again, either through evaporation, you lead to this issue of desertification, where areas don't have enough water, so they turn from luscious and green to essentially deserts. So, and because of more evaporation, more water stress, we're actually likely to see an expansion of deserts. So in Africa, for instance, the Sahara Desert is expanding year after year after year. So it's getting bigger. It's going to cover more of the continent of Africa. But there's actually kind of a cool thing about this. I don't know if anyone has seen this, but there's many countries in Africa that are trying to build a great green wall of trees to try to prevent the Sahara Desert from expanding. So humans, we do lots of cool stuff, but there's only so much we can do. So that's rain. Next up, we have changes in nutrition. And so warmer climates means greater water stress, and that means less crops and less crop variety. So if crops are stressed for water, they don't produce as much food. So if I have a parcel of land and I grow corn on it and it's well watered, I get a lot of corn from it. But if I don't water it as well, I get less corn. That's just the way it works. The other thing is it leads to less crop variety. So some crops, like corn, require a ton of water. So if there's less water, it means you can't really grow corn. And that would just be, frankly, that would be devastating for the United States because we rely so heavily on corn for everything. But that's the idea. Warmer climates, less crops, less crop variety, less nutrition. But interesting speaking, with less crop variety, this is kind of a big issue in places that are already very dry. So you think about Africa, right? Or areas that are, less well-off economically, that are less likely to adapt. And this encompasses about 2 billion people at present day. This becomes a problem because so many people are already malnourished, and less crops because of less water. Well, that means more people are going to go hungry, and there's already too many people suffering from malnutrition across this planet. Now, the other side of this is the crops actually become less nutritious under high CO2 values. This is sort of a weird thing. If you want to take a peek at this article from Harvard, it does a really good job discussing it. But one of the weird things we've noticed when we start to look at how crops respond to higher CO2 is when you add more CO2, it doesn't just affect yields because of food or weather or whatever like that. It actually makes food less nutritious. So if you increase CO2 projections to the levels we expected to see in 2050, crops will lose 10% of their zinc, 5% of their iron, and 8% of their protein content. And there's all sorts of other things that vary between these crops. So some crops will lose starches, they'll use other vitamins and minerals. Crops become less nutritious when there's more CO2. I could not explain to you how that exactly works, but it is a phenomenon we know exists. And sort of thinking about this, it's not a big deal here in the United States, right? We eat thousands and thousands of calories every day, but places that are already strapped for calories, this will be a huge deal. If they're growing less nutritious food and if they're already starving or they're already experiencing malnutrition, well, it's just going to make things worse. And again, not a huge deal here in the United States, but places that rely more heavily on crops and grains, it will be a much, much bigger deal. Another reason is if you love coffee, climate change should scare you as well. And so this is a nice article from InsideClimateNews.org about this really fascinating study that came out a few years ago about how climate change is going to affect coffee. And I'll let the scientist do this talking here. He says we should be concerned about the loss of any species for lots of reasons. But for coffee specifically, I think we should remember that the cup in front of us originally came from a wild source. We think at least 60% of lost coffee is conservative, unfortunately. He said, noting that other chief threats, deforestation and limits by distribution, can be worsened by climate change. All those things are very tightly connected. So if you love coffee like I do, climate change should really concern you because globally we're losing species of wild coffee and it's becoming much harder to grow coffee plants, coffee trees, year after year because coffee doesn't do really well in dry, warm areas. It does well in wet, warm areas, but not dry, warm areas. But again, as climate changes, these places are getting drier, we're going to see less coffee. And that just makes me sad because I'm sitting here giving this lecture and I have coffee next to me and that makes me very sad. If you don't like coffee, we're seeing the same thing with actually with grapes and wine and hops and beer. So just as a note, if you're not a coffee drinker, it does affect beer and wine as well. As I mentioned, it's going to change. Climate change will change weather, and it's going to change things affecting sort of some things that we've sort of already discussed, but these include having more severe droughts. So California was in a drought for a decade straight because of climate change. Australia, again, with all those huge fires that they were experiencing, again, they were experiencing a huge drought. Massachusetts, up until last year, was experiencing a 5-year drought. So droughts are going to be much more common. We expect to see much more extreme precipitation events because of warmer weather, more evaporation, more water in the atmosphere, thus more extreme water events. Climate change, again, sea level rise, more coastal flooding, and more heat waves as well. So all these things are a thing. We also expect to see more hurricanes. So this hurricane season is expected to be the worst hurricane season on record in terms of tropical storms and hurricanes. And we expect to see, because of climate change, more and more storms and more severe storms. So again, just sort of ignoring all the effects this has on biology, this is going to have a huge economic impact, right? Think about how much it costs to recover from Hurricane Maria or any of the other hurricanes that have hit us, right? Billions of dollars. So this has an economic footprint as well. But as I've sort of alluded to thus far, there is this huge moral and ethical issue. And it gets back to this idea of environmental justice. Those that are most likely to suffer are those in the poorest areas of Africa, Asia, and Latin America. And sort of the unfortunate thing about these areas, the places that are poor, as I showed you, they release the least amount of greenhouse gases. So, sub-Saharan Africa, very, very poor, very, very little greenhouse gas. Remember, the places that emit the most greenhouse gases are places like the United States, China, places that are wealthy. But the people that are going to suffer the most are going to be the poorest people. And not just in Africa, in Latin America, but even in our own country. Places like New Orleans, right, that the South, right, places that are very, very poor are going to suffer the most. And as things get worse, we're going to get what are called climate refugees. And these are people that are leaving their area and they're going to someplace else because the climate is going to make it so impractical for them to live in their area. Now, you might think, oh, this is not something we have to worry about now, but we're actually already seeing this direct effects. Part of the reason why we're seeing the civil war in Syria is partially due to water shortages, partially due to climate-related events. So the millions of people that have left Syria, part of them are climate refugees. And I think it's important to note about how sort of dire the situation is in Syria is that everywhere around it is sort of had a really difficult time taking in some of these refugees. And so just picture this at a sort of a global level where you have millions or potentially billions of climate refugees. How are we as a sort of a society, as a global institute, going to handle this, right? Because, in the United States, we have an issue with immigration. What's going to happen when that immigration level spikes because of climate change, right? And so what is this going to look like in the future? And there's this other issue here as well, as what we call intergenerational equity. And this means that my mom is not going to suffer the worst issues of climate change, but I am, my kids are, and my kids' kids, right? So the old people who did most of the sort of put most of the CO2 into the atmosphere, they're not going to suffer anything from it. But we, my generation, the generation that comes after me, and so on and so forth, we're going to suffer the worst. And so there is this huge moral and ethical issues around climate change. And that's really unfortunate because people that, were kicking you can think about someone like Jeff Bezos, who has a huge climate footprint. He'll likely be a trillionaire at some point. He's not going to be affected by climate change at all. Even though he's contributed a huge amount to climate change, he's not going to suffer at all. But people that have done nothing are going to suffer hugely. And that's really, 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 really shitty. to put it no other way, it really is. So that's the sort of the things that are going to happen. There is this, I mentioned, it's a controversial issue, and it's a controversial issue like vaccinations for no other reason than people want to make it one. The science behind climate change is in agreement. If you look at 98% of papers that have been published on the topic, they're all in agreement. Climate change is happening. It's all caused by humans. We need to do something about it. Scientists are in agreement. Like vaccination, like many, many other topics, scientists are in essentially unanimous agreement. So it's happening, it's caused by humans. And more and more, I'm thinking mostly in the United States, most of the rest of the planet accepts climate change as a thing. It's caused by humans. There's less of a debate. But here in the climate change, people are still, here in the United States, people are still confused about climate change. And it's really just this idea of a belief. It's not, we look at this, 98% are in agreement. It's really a belief, right? All the evidence is out there, but it's really become this identity and a political philosophy. If you just went off the evidence, there's no reason to believe climate change isn't a thing. But again, it's become this belief. It's become a political identity. And this sort of, the interesting thing is that as a political position, it's new, right? It started, we knew climate change was happening in the 90s, but it was a sort of a far off problem. But when the 2000s rolled around, it started becoming a political issue. You could start seeing it around the first George Bush Jr.'s W's administration, right? Climate change is becoming political. But you can also see that, Clinton and George Walker Bush, they did award medals to people studying CO2. So that was again prior to the politicalization and this identity or this belief that climate change was not a thing. And it is highly politicized. And you can look across our political sort of leaders, whether it's our president, whether it's senators, past presidents, it is a highly politicized thing. And it's not just politicized from, our politicians, but it's also media personalities. And so I love this tweet from Stephen Colbert. He's one of my favorite comedians. If you don't watch The Tonight Show, it's a really, really awesome show to watch. But I'll stop glowing about how much I love Stephen Colbert. But he says, global warming isn't real because I was cold today. Also great news, world hunger is over because I just ate. And so I say this, it's funny. And climate change is kind of a dreary topic, but it is heavily politicized. And it's become more of an opinion as opposed to this is what the evidence shows. And it's also, some people, it's a matter of perspective. You typically tend to conform to beliefs around them. So if your parents don't believe in climate change, it's likely that you also don't believe in climate change as well, even though the evidence is there. But regardless of how you feel about it, that the science is concrete. And again, and there are all sorts of other conspiracy theories out there about climate change as well, just as a note. But the sort of interesting thing about climate change, it does, maybe governments aren't responding to the way they should be, but businesses are. Businesses are becoming more and more environmentally sustainable. It's being part of their marketing advertisement. So like I see commercials when I watch Hulu, I see them for sustainable businesses all the time because it's becoming something people are investing in, making priorities. We're also seeing insurance companies becoming, factoring climate change, factoring sea level rise into their profit margins. How is it going to affect them going forward? We're also seeing companies and universities, churches, things like that, divesting from fossil fuels, trying to get away from causing the problem. We're also seeing the United States military recognizing that climate change is one of the most important problems facing our national security, as well as the national security of other places in the world. Because remember, the refugee problem in Syria, partially due to climate change. Now, with that out of the way, what can we do about it? There's all sorts of things you can do to change your habits. And they range from changing your diet, changing how you get your energy, getting renewable energy versus fossil fuel-based energy, changing your appliances, changing your cars, changing how you get around. Those are all things that you can do to sort of do it. One of the ways that's really, really effective is thinking about what you eat. So for those of you that never tried a Beyond Meat patty, they're actually pretty good, but they are much better for the environment. So as you'll notice, they produce less CO2, they produce less methane, they require overall less energy use, less land area, and they require way less water to do it. So they're much more environmentally friendly. And again, changing your habits, the way you eat is one way of doing that. You can also consider donating to climate change projects or offset carbon emissions by donating to, I don't know if you guys saw Team Trees, or was it earlier this year? They try to plant 20 million trees, things like that. So that's something you can also do. And it's also thinking about your choices. And sort of the reality of it is the vast majority of greenhouse gas emissions can be traced back to 100 companies. 100 companies. 70%. So 70% of the problem, 100 companies. Now, these companies are doing what they're doing because they're making money, right? That's how capitalism works. You sort of forget the environment. You do things to make as much money as you can. Now, the only way we can change these companies is by putting commercial pressure on them. So not buying from companies that don't do things sustainably, that don't do things that produce less greenhouse gases. And so I like this quote from Richard Heed. He says, if you're choosing a new dishwasher, it may make sense to get one that's more energy efficient. It might cost $80 more now, but you can get that back in lower utility bills. And as we're buying these things, we might consider where they're produced. And by choosing what we buy to be more efficient, less climate change inducing, it'll cause these companies to change their behavior as well. And one of the things about you see from these companies is they put the issue directly on you. And the wealthy do the same thing. None of us are extremely wealthy. At least I don't think any of us are extremely wealthy. My guess is you probably wouldn't be going to UMass Boston if you were extremely wealthy, but maybe you are. I don't know. But as I mentioned, the wealthy and these large companies cause the majority of climate change. And so, but they do like to put it on us. But at the end of the day, the wealthy are putting way more CO2 into the air. These companies are putting way more CO2 in the air. But we can't do anything about the wealthy, but we can modulate the behavior of these large companies. Changing your buying habits can really, really make a difference. So with that, again, I guess the final other thing I will say, if you do care about climate change, you do care about the environment, voting, at least here in the United States, is one of the best ways to make a difference. Putting people in Congress, putting people in the White House that will essentially be tackling this issue, because we've been kicking it down the road, and it's to the point where we really can't keep kicking it down the road. So if you care about climate change, if you don't want to see the Earth go to the direction I've showed you, vote for people who want to change and tackle climate change. Because again, it's not just a science thing. It's not just an environment thing. It affects everyone, and it's going to affect the poor. It's going to affect the sick, the elderly. It's going to affect everyone. So it's really not just a science thing or a business thing. It's a humanitarian thing as well. So, and then you can also demand that they're financially responsible, as your classmate says. That is true. Making people be more responsible, make them develop new technologies, force them to tackle climate change. You can look at companies like Apple, right? Their main campus, where they have a lot of servers there, it's completely green now, right? And that's because Apple made the investment, because their consumer base didn't force them, but they heavily encouraged them to go in that direction. So you can make a big difference by pushing on these companies. They're not making money. They're going to try to find ways to make money, because that's capitalism. So just a few sort of wrapping up points. Temperatures are higher now than they have been in the past 1,000 years, and it's all due to increased CO2 and greenhouse gases. Remember, those are linked together. The important thing to remember with climate change, it's happening faster than it has ever occurred naturally. Remember, it does change naturally, but the rate at which we're changing it has never been seen. A 5-degree change in temperature of the planet should take 20,000 years, but we're doing it in 200. And all the science agrees climate change is happening. We need to reduce emissions, and it's something we need to do now. It's not like that cartoon I showed you at the beginning. It's like that cartoon I showed you at the beginning. It's not a 50-year from now problem. It's a problem that's directly in our sightline, and we need to do something about it now. And it is all due to humans. Don't let anyone try to tell you otherwise. The science is in agreement. It's caused by humans. And it's really all hands on deck here. It's not just you and me. It's not the government. It's industries. It's everyone. Because this is our economy is so heavily dependent on fossil fuels, and we need to move sort of not just to tackle climate change, but also for the stability of our economies to move towards a much more sustainable sort of tract, which will in turn again help address climate change. So that is going to be it for today's class. I hope you guys learned something. I hope you got a little angry, or I don't know. I hope you at least learned something. If you have any questions, you have any concerns about what you heard, if you want to know more, please let me know. I'm always happy to talk about climate change, because it is really the most important issue over time. It's not immigration. It's not terrorism. It really is climate change. Climate change is the issue of our generation. And you guys are young. Well, as far as I know, I know UMass Boston has lots of older students, but it is some problem that's going to affect you as potentially younger individuals the most. So take advantage of the knowledge you have, keep doing research, and push for a future that you want. Maybe you don't care. Maybe you want to keep doing what you're doing, and that's on that. You can do whatever you want. But given what I told you, I hope you would sort of push for those things. But anyways, with that, that's going to be the end of the class. Any questions, as always, I'll hang around. If not, you can send me an emails. And as a final note, your exam will be available for you tomorrow as well. Tomorrow. So I'll see you guys tomorrow.